this is some short brief about what I'm doing.
Well, thank you. Sounds very interesting.
Yeah.
And also thank you for the invitation to be able to present myself. I fully support sustainable goals and sharing knowledge among all scientists and actually everybody.
Yeah, thanks for joining us anyway.
Thank you very much, Michael. Or how can I pronounce your name?
Michael, anything goes.
Yeah, Michael. Yeah. You're very kind to accept our invitation and sharing knowledge.
You're very kind to invite me.
Thank you.
Thanks, Michael. Yeah, because today we will focus on really on magnetic simulations. Yeah, from the materials to the devices, and we've been here some use case as users the PyMap tools from Mikko that he developed. But Mikko, in our network, really we cover many topics. So in this meeting, we also invited all members and also students from the network. But let me focus on some groups that's really working on magnetic materials, magnetisms, also device and materials. I would like to move to Professor Diep. And Diep, can you give a short introduction about you? Maybe just 1-2 minutes shortly.
Yeah. Hello.
Thank you.
Hello, everyone. I'm sorry that I just got the COVID. So my third day of COVID, that is why I feel very tired. But I try to listen to you, but I cannot speak much. So I'm sorry for that. Yes, I am actually working as an associate professor in France in one university called École Normale Supérieure, Paris-Saclay. And my research focus on different topics, but yeah, one of them is related to magnetic resonance. So I did my postdoc 10 years ago concerning the single spin manipulation. And recently I try to use some kind of laser technique to realize some kind of magnetic nanostructure. I try to mix magnetic nanoparticle into polymer material and try to pattern some magnetic structure and use electromagnetic field to control the movement of magnetic structure. So that is one of my research direction, which has connection with what you will present today. Otherwise, I also have other research topic like quantum optics by working with quantum dot in order to generate single photon and manipulate single photon using photonic structure. And another topic I also want to develop and work on is the plasmonic nanostructure. And recently, I also collaborate with one Vietnamese American scientist to realize some kind of magnetoplasmonic structure for sensor applications. So that is what I am doing as a research, and thank you very much for the talk today. I hope that I can learn a lot from the talk concerning the simulation using different kind of software. Thank you.
Thank you, Anh Diep. Yeah, I could see here chị Giang. I would like to introduce yeah, Giang Do. I would like to say that chị Giang to Mikko. Chị Giang has a group also working on magnetic sensor in Vietnam. In my university where I graduated, we have the small green room also with the a young scientist, anything very young and but very motivated Professor Chị Giang. So Professor Giang, can you give some short introduction about you, also about the group and the topic that you are working on?
Yes, okay. Hello, everybody. Yeah. is very good.
Sorry, chị Giang.
Organize this seminar because my and can
Sorry, chị Giang. We can't hear
can
you
you
well.
hear me?
Yes, now it's
Yes.
okay.
Okay. Let it's okay. Now it's okay.
Now it's okay.
Okay. Okay. Yeah, today is our group in our university. I think all of them stay here. Our topic focus on the nanomagnetic material and magnetic sensor, and we focus many effects for magnetic sensor in, for example, giant magnetoresistance, magnetoelectric effects, and also we focus on multiferric. We have several kind of magnetic sensor, and we also have some package sensor for commercialized. And but we most based on the experiment. We are not expert in simulation and theory, so we found that in this seminar tonight. So we will hope that we will learn a lot from the tool you give, so we can develop for our research. Yeah, that's all.
Thank you very much, chị Giang. So also thank you other colleague, also Stefano from our company, and also Pella, our former colleague. But I think it's time it is short. We will give introduction to one or two other colleagues who are working on magnetic materials and also devices. Maybe Bernd, can you give a short introduction about you?
Yeah, can you hear me?
Yes, perfect.
Good. Yeah, I'm Magpylib. I'm working for a university in Carinthia, and I'm a former teammate for Michael Ortner. And I'm excited to hear his newest development on the Magpylib program. And I'm still working on electronics and a PCB simulation task for the Carinthia University of Applied Science. So I don't switch on my camera because I think my data bandwidth is not good enough for my home office.
Thank you. Maybe Stefano, can you give a short introduction about you?
Yeah, can you hear me?
Perfect. Yeah.
Yeah, my name is Stefano Lumetti. I am been working at Silicon Austria Labs for the last 3.5 years, and I am a colleague of Michael. We work together in magnetic projects, and I mainly deal with the experimental part of our research activities.
Thank you. So Bella, can you give a short introduction about you as well? Bella? Then I will move to Phan Anh. Phan Anh also working on many on modeling and simulations, and he already went through the PyMap package, and he really interested in this. Also, his team. Phan Anh, can you give a short introduction about the research, the interest? I'm sorry, it's because Phan Anh has a small baby and he's now at home and he can't speak. I'm really sorry. Maybe anh Vũ Nguyên Thức, can you give a short introduction about you?
Tux also member of our group, the same
Okay.
topic.
Okay,
Yeah.
that's good. Anh Tuấn Nguyễn.
Yes, actually, hello everyone. My name is Tuấn, and currently I will lecture at Lake Udon Technical University based in Hanoi. And my topic mainly about soft-enhanced magnetic nanocomposite. It's some kind of magnet. And currently I work with Giang at the postdoc. Đỗ Giang at the postdoc with her.
Very good. Yeah. Hồ Anh Tâm.
Hi everyone, my name is Tâm. I'm from Vietnam National University. I'm a PhD candidate now, and my major is about laser application, and my PhD thesis is about magnetism. Thank you.
Thank you, Tâm. I'm sorry, I also don't know all of other colleagues who also working on magnetic material or devices. If you are working in the same topic, please raise your hand and introduce yourself shortly to Mikhail, and then we have better interaction later.
Actually, I'm focused on biomagnetism. I'm trying to make some microfluidic integrated with magnetic sensor to detect some bio element for some bio application.
Thank you, Hồ Anh Tâm.
Yeah.
So any other colleague that's working on magnetics material device?
Excuse me?
Yes.
Actually, my major is about laser application, so I'm trying to use laser to make some microfluidic channel, some simple method to fabricate microfluidic system, and another field that I'm trying to use some method, some simple method to make magnetic sensor, like based on laser and based on wet etching, so that I can make a very cheap device and without clean room, like that.
Thank you, Tom.
Yeah.
Yeah, then now I think we will give time to Dr. Mikhail. Mikhail, are you ready?
Yeah, absolutely.
Okay, short introduction about Mikhail. Mikhail is working in a magnetic MEMS group. He now is the interim coordinator of the team with six colleagues, right, Mikhail? Before Mikhail also working on really on in Vietnam we call this condensed matter physics, and also covering from theoreticals and also to simulations. And his group now dealing with magnetic sensor for many applications, but many for automotive, also for consumer devices. I'm very happy to know and to work with Mikhail. We're working almost in the same big group, and yes, next to each other. That's in the same office almost, and we talk daily, every day. And one day that I just expressed to Mikhail that I just shared to Mikhail that we have one network that's we often have knowledge seminar, and really encourages not only to experienced people but also young people to join, and not only to share for the collaboration, but also to encourage the young colleagues to learn new things, to exchange the knowledge, and also for your future collaboration. If yeah, we really can see a complementary experts from each team, each topics that we can work together, especially the colleague working in Europe. We can have the one base, and also in US and also in Asia, also from Japan, Korea, Taiwan, and Vietnam. And Mikael really happy to support it, and from his side, he really wanted to support, to share what he experienced, also to motivate his young colleague, young student to work, also to learn on not only on magnetic material sensor, but also really particularly on his tone simulation tool, which is really open to it is open. So in Vietnam, Mikael, you noticed we really limited in the funding, and one of the big problems is just most of the license simulation license is really expensive, which is really cannot cover by funding. And the colleague also tried to work with yeah, either an analytical model, or they have to collaborate with external yeah, scientists, also other network to have a simulations. But this is very good chance that yeah, we can explore the tool that Mikael and his team developed based on Python, which is really free and also flexible, quite huge flexibility that to import the requirement. And also you can also say it with students to motivate students to learn Python and to do some simple case study. And Mikael, can you start and give us a short introduction about our team and activity before starting to introduce Python's Magpylib?
Yeah, absolutely.
Okay, thank you.
Yeah, so basically we are a small team working in applied research on magnetic position systems and magnetic sensor systems in general. And so basically half of the work that we're doing are focusing on macroscopic position systems that I will also introduce during the course of my talk. And basically in the second half of the team is working on micromagnetics and micromagnetic sensors, development of micromagnetic sensors. And we are fabricating our own AMR sensors, and we're trying to combine the two. So we are trying to bring the position systems down to the microsystem. And this means sensor development and sensor integration. Yeah, that's it. Shall I start with the talk?
Thanks, Mikael. Yeah, please.
Yeah, okay. I'll share the screen. Do you see now my background?
Yes.
The slide set.
Perfect. Yeah.
Yeah. You see the slide set now? Full screen. Yes. Wait, I just have now this interface.
Full screen. Yeah. Here. Very good. Yeah.
It is a bit in the way. Okay. Okay. Yeah. You can see everything.
Perfect, Mikael.
Okay, well, then I get started. Just let me check the time so I don't go too much over time. Yeah. So, yeah. So thanks for the invitation, and thanks for letting me present the Magpylib package that I've developed over the last years. You know, Magpylib, just in short, it's a Python package that allows you to do macroscopic magnetic field computations. There are a bunch of open source packages out there that allow you to do microscopic computations, but not so much for macroscopic computations. And our ansatz to do these computations is actually quite unique, as I will show them during the talk. Before I talk about the package itself, I would actually like to tell you a little bit about the background, where it comes from, and why this is interesting. And basically 10 years ago, I started to work on magnetic position systems. What is a magnetic position systems? It's basically The idea is just that you determine the relative position and orientation between a magnetic field sensor and the permanent magnet to determine some kind of motion in some mechanics. The magnets that you use, they're normal macroscopic magnets that you would buy from some kind of off-the-shelf manufacturer. Yeah, they will probably look like this. And the sensors that you would buy, they are mostly industrial sensors, like here, the sensor from Infineon, which is fully integrated 3D Hall sensor device. But there's also a lot of position sensing happening with AMR technology, GMR technology, TMR technology. I've even seen some flux gate around for these kind of purposes. Yeah. For you to understand what kind of motion we're detecting, have a look at these two pictures over here. Yeah, what you see here is the BMW iDrive module. Yeah, I don't know if you have a BMW at home, if you're earning this much. In any case, this is the central steering unit of the BMW console. It features a kind of joystick-like motion. You can tilt it in two directions, and you can also rotate the knob, and you can also press the knob. And this whole functionality is covered in the original BMW with a bunch of sensor technologies. There's some optical sensors, then you have this rotation encoder, and then you also have this push button, which is capacitive. And what we try to do, so basically you have this kind of mechanic, and what you want to do is you want to determine this with magnetic sensor technology. And in this specific case, you can here look through this window into the inside. Basically, we just glue a bunch of magnets to the mechanics of this iDrive. So when this knob rotates, then these magnets will also rotate. Below, we have two magnetic field sensors. And from the readout of the magnetic field sensors, we determine the position of this knob. And we can determine the full range of motion just with a few magnets and a bunch of magnetic field sensors. So this is, of course, much simpler, much easier, much more robust to use than, let's say, previous technologies. And this brings me directly to the advantages of the magnetic sensor systems. You know, they're extremely robust with respect to dirt and oil and temperature, water, no problem. They have very long lifetimes because you have contact-free operation. Yeah? The magnet, it just moves around. You don't have the usual problems that you have with a potentiometer that it will die after half a year or so. So long lifetimes means really however long your sensors will live, because the magnets, they will not go bad typically. You have potentially very high resolutions and fast response times, but the main reason why magnetic sensor systems have become so extremely popular is because they are cost efficient. As I just stated, you just have this sensor. The sensor, it doesn't cost anything. It costs €1. You have a magnet, it costs €1. And this is what allows you to penetrate the market. When technology is cost efficient, then it will be picked up. And nowadays there are hundreds of applications. Yeah, these are just some applications from automotive that we are very familiar with, like the gear shift position, steering wheel angle, torque, blinker lever position, motor position, ABS, wheel speed, window lift system, and so on and so on. Yeah, there are more in a modern car. There are now more than 100 of these magnetic sensor systems integrated in order to determine, all these kinds of properties and motions that you need. There are also some downsides, disadvantages to the magnetic sensor systems. And one of them is that there are very few good concepts out there. In principle, all you have are linear positions and rotary motions. You can also do some joystick motions, but in principle, a joystick is just a 2D linear position system. And you have side shaft applications, but in principle, it's also just a rotary system. And what's even more funny is that in principle, the rotary system and the linear position system, they work in the same way based on the same mathematics. It all runs through this Arcus-Tangens function. I don't know if you are familiar with this concept. And so in principle, there are very few concepts out there, very few good and stable concepts. This concept that there is quite versatile, but it could be better. And and then magnetic sensors are, of course, have problems with external stray fields. For example, from cables, it's a huge problem with modern applications when it comes to the electric cars. You have cables that run a few amperes, few hundred amperes, a few thousand amperes even, and then you're going to have very strong stray fields that will influence your sensors. And the biggest downside, and this is also the reason I think why I have this job and why I still have it after 10 years, is that each case requires its own design. no linear position systems looks like the other. There are rough guidelines, but in principle, you always have different requirements. You always have different air gaps, and this always needs a different and specific designs. So how do you design such a system? How do you design this? In principle, what I would do is I would do some kind of FEM environment, you know, like ANSYS and COMSOL. As you say, they're very expensive, but let's assume we have this, and I want to simulate this. It's still going to take quite a long time. Talking about I don't know, minutes, hours, days, and so when you want to do system development, it will just take a long time. Optimization is basically impossible because you have a lot of variables that you want to vary, that you want to touch, and tolerance analysis it's just not feasible if you work really with FEM. They cost a lot of money, big problem, and if you want to implement your own, then it really requires a lot of time, extensive theoretical know-how. You don't want to do that. So after playing with a bunch of these systems, we realized at some point we are always doing the same. Basically what I just explained here. All the systems are kind of similar, and all the magnet forms, they're all the same, cuboids, cylinders, and this kind of stuff. And at some point we realized maybe analytical solutions are a good alternative to these numerical models. And I think most of you are aware what an analytical solution is and what a numerical approach is. Let me just review it briefly. When I talk about an analytical solution, I mean that I have just an expression for the magnetic field. I evaluate this expression, and this typically will take the order of a few microseconds. And I get these expressions simply by taking an integral over the magnetization distribution. Or in case of homogeneously magnetized magnets, you just integrate over the surfaces. And so basically I just have to solve these integrals for specific forms. I get expressions such as those, and then I can use those to compute the magnetic field very fast, very efficient. Of course, I will be limited to simple geometries, but there are a bunch of solutions that exist in the literature. And of course, I'm also not going to have material response. This is as opposed to the numerical methods. Here is just an outline of how FEM works. In principle, you know, you have your magnet, you want to compute the magnetic field here. So what you do is you just go to some finite volume, you implement a boundary condition, you mesh the whole system, you split it up into small parts, and then you transform the differential equations into a set of linear equations. And the coefficient matrix is basically the size of the coefficient matrix is just going to be the square of the number of elements that you have. The precision that you have, of course, goes down with the element size. So this is computationally expensive. And however, these are very good all-purpose solutions. You can work with arbitrary geometries, and there are a lot of programs available, like COMSOL, ANSYS. There's also an open source solution, but it just works in it's just in 2D. Yeah. So after playing around with this for a while, we realized we are always doing the same geometries, the same forms. And then we start to think about the analytical solutions. And when I talk about the same forms, I also want to point out these new DIN specifications. These are new German specifications for what kind of magnets you have in magnetic position systems. And you can see also here that it's always the same repeated forms. It's cylinders, it's hollow cylinders, it's cuboids, it's superpositions of multiple cuboids stacked together in various ways. And the biggest problem when you work with analytical solutions is, of course, as I said, no material response. This means you cannot do soft magnetics. And the big problem with soft magnetics is that, you know, you magnetize the soft magnetic material, and then then you have additional magnetization. This will change the magnetic field, and then the analytic solution will just be completely wrong. However, it turns out that in magnetic position systems, you really want to avoid soft magnetic materials because they give external stray fields, for example, from cables, a position dependence. And when that happens, you cannot compensate for external stray fields anymore when you do sensorics. So soft magnetics are generally avoided in magnetic position systems. And with this, the analytic solution is really an excellent alternative to work with. So back in 2012, when we've been working on this for a year, I put together, so if I would have made a Christmas wish list, this is what it would have looked like. I would have really loved to have properly implemented and reliable analytical expressions. They should be performant, they should properly vectorized, efficiently coded, they should be stable everywhere. I don't want to think about numerical stabilities in special cases. And of course, they have to be validated. So I want to know, I want to be able to compute fields. And yeah, it's a lot of effort from the equation that you have in a paper to bringing it really down in a program properly. And then what I really also want to have is, I want to be able to let's say, make coordinate transformations in an easy way. I want to have like an object. The object should generate a magnetic field. I move this object around, and then I have, you know, it's just relative positioning and a relative orientation to transform from the coordinate system of the source to the coordinate system of the sensor. But everybody with a technical background has done this, and you all know how prone to error this is. It's very fast to make errors. So I just want to have this. I don't want to think about this anymore. And yeah, so I want to have some kind of position and orientation interface to transform between reference frames. And then what I also want to have some kind of graphic representation that allows me to know what I'm actually doing. And if I have all of this as a Python package, that would be ideal. It should be open source. It should be free to use for everybody. The installation should be easy. I don't want to think about this. The interface should be very, very easy. I want to think about my system developments. I do not want to think about implementing analytical expressions and coordinate transformations, this kind of stuff. And it should be integrated nicely into the Python ecosystems. This means if, like every scientist, I would be working with NumPy, SciPy, Pandas. This is basically what the library should do. And it should also work with all the contemporary graphical backends like Matplotlib, Plotly, PyVista, Mayavi, and other packages that many of you are for sure familiar with. So, and this is the Magpylib project. Yeah, so Magpylib is now an open source community project. We're on GitHub. You will find us on GitHub, and you can install the Magpylib package with pip or with conda like every other package since 2019. The computation is based on the analytical solutions, and we also did a lot of testing on how accurate they are. And it turns out that if you use good materials, samarium cobalt, neodymium iron bore, ferrite materials, the error that you make in computation will be below few percent. And if you compensate with demagnetization factors, you easily get down to few promille error. And yeah, and this is usually, in most cases, this is more precision than you will ever need. The solutions are extremely performant. The way we've implemented them, the computation time typically takes a few microseconds for the base forms. The code development time is minimal, so we really spent a lot of time thinking about how to make such an interface nice and easy to work with. Of course, we're limited to simple geometries and superpositions thereof, and we don't really have any material response. So you do have to also think a little bit about in terms of you need to have some magnetic knowledge. But in principle, I mean, there are the advantages over the numerical methods. There is no meshing involved. We don't have to think about boundary conditions. We don't need to do any error analysis, numerical error analysis. And you don't need any numerical computation know-how. You just use the package, you get the field out, you can be sure it's correct. And the interface that we've been thinking about so much works in the following. You just define an object. The object is, for example, a sensor, or the object is some kind of magnet. The object has attributes, properties like position and orientation, and also like the magnetization of the magnet. You manipulate the object. You can move it around. You can change the position. You can generate paths. And then you simply compute the magnetic field. And in between, you also have the show command that allows you to show the system. But I would actually, instead of talking about it, I would actually just like you to show the code because it's very readable and it's quite self-explanatory. So this is really the base syntax that works since version 1. You want to have a cuboid magnet. This is how you define it. You define a cube. This is an object based on the cuboid magnet class. You say, I have this magnetization, I have this dimension, and this position. All units in Magpylib are in millitesla for magnetic field and magnetization, kiloampere per meter for the H field, millimeter for any kind of positioning, and degrees for any angle. Of course, you have all these scaling properties, but if you don't want to think about it, just stick to those units. And you can see, so what this does is it creates a magnet, and basically it's a magnet like this, 1, 2, 3 millimeters. The center of the magnet is located at the position 0, 0, -3. This is what you get. We manipulate this magnet with move and rotate commands. You can also just change the position, but this is a demo to demonstrate these methods. Move method, relative motion by 6, 0, 0. We're moving the magnet over here. Then we rotate the magnet by 90 degrees about an axis that points in Z direction, anchored at 0. So it's just Z axis and ends up over here. Yeah, so we move sources around. We can generate a graphical output with the show command. It will just tell us what do we have. And if I call this, then basically something like this is what I'm going to see. What I forgot to mention is, of course, the magnetization. You can see the magnetization in this case is the color code. Yeah, so this is a magnetization in Z direction. And after this, so I've generated my system, I placed all my magnets, I have my coils, wherever everything is placed. Then I want to compute the magnetic field. And I want to compute it now on a grid. So I just simply define a grid. This is a line of code that defines a grid in the YZ plane. It's basically this back plane over here, and it includes the magnet on the inside. And then I compute the magnetic field with a single command, compute the field of the source, which is in this case a cube, at certain observer positions, which is in this case the grid. And the outcome is then just going to be a large array of the same shape as the grid, but it's just going to be the magnetic field values. And here we can just plot them using Magpylib stream plot because it looks good, and then you will see something like this, which is the expected field that you have when you have a magnet in here, and this typical dipole field, that you get. Yeah. This is the fundamental syntax. Yeah, so you have you want to work with magnets, you want to compute magnetic fields. This is what you can use. Very fast, very easy, fast computation times, automatic vectorizations, performant implementations. You just use it and you don't have to worry. And that's basically the goal of Magpylib. Of course, we don't just want to do that with cuboid forms, but there are a bunch of base forms that we have implemented and that are available in Magpylib version 4. It's the cuboid, it's the cylinder segment, and the sphere. Yeah, those are all magnets, permanent magnets with homogeneous magnetization in arbitrary Cartesian directions. We also have current filaments, which is just a line current at the loop, and also a sensor class that allows you, to create relative position rotation between a sensor and an observer. With these base forms, you can see that we're already covering half of the base forms that are required for the position systems, which was the original goal. But of course, in magnetostatics, you can make use of the superposition principle. This means that the magnetic field of two magnets is basically just the sum of the individual magnets. So you can construct complex magnet shapes by just putting them together. This, of course, only works if you don't have material response. And in this case, you can just create more forms, like, for example, linear scales or octopole magnets, or rotary encoders, coil systems, planar coils, whatever you want to create. And Magpylib supports this with a fundamental class that is the collection. The collection class allows you to group multiple magnet objects together and to manipulate them as if they were a single object. So move and rotate operations will apply to the whole collection, while you can still address individual objects in a collection. And if you, down here is the code that shows you how this linear scale was created. It's in principle, we just define an empty collection, we make a loop, we generate the poles, and we just add the poles at every instance of the loop. And and if you want to compute the magnetic field, then the collection will be treated like a single magnet object. There's a second fundamental feature in Magpylib, to facilitate working with this, and those are paths. Position and orientation attributes of magnets can be paths, meaning they are not single positions, but they can be vectors of multiple positions. And these can either be created, so you can see it down here, they can either be created by simply assigning the position attribute to a path, as you can see here, like a linear path that goes from the origin to the position 400 in 30 steps. It's basically this thing down here. Or you can also use move and rotate operations to append or override existing paths. Here we're just appending the path 000 to 004 in 30 steps. And this is, of course, relative appending, so relative to the last position of the object. And basically, it's this part of the path. And as you can see up here quite nicely, with Magpylib, you cannot, the graphical output that you can create, in this case with the Plotly backend, can do animations. If you have paths, the paths will be shown here, but you can also create it as an animation. I know this is just graphically, but I find it really important to be able to show your ideas to other people. So it will make it much easier for them to understand. So I think there's a lot of value in this. And finally, you compute the field. You compute the field again. You just call the getB command for the source, which is in this case the cube, and the sensor, which is in this case static. And the field computation will compute the field at every position of your path. And then you can just plot it again with Matplotlib. You will get something like this out. You can see at the first 30 path positions, you have this magnetic field at the sensor. And for the next 30 path positions, you then have this. And you have this small discontinuity here because the path is, of course, not continuous. Yeah, so this already concludes the fundamental the fundamental functionality of the Magpylib package. Everything beyond this is more or less just let's say either advanced or some candy, so to say. We have graphical styles, so you can customize your graphics, your object graphics as you like. Please refer to the webpage for this. There are numerous examples there. You can include CAD models just for graphical representation. Like here, you can see a nice sensor model. We have a high, so we have possibilities for customization. Yeah, there's a custom class. For example, you're a user and you want to introduce your own class with your own field computation. You can do so using the custom class. You can create an object that then fully integrates into the Magpylib system, or this position and orientation interface, but the field computation will be done by the class that you are, by the function that you are providing. And also you can make the graphical representation as you like. Like here you can see I create a quadrupole field and make this graphical representation. This will fully integrate into Magpylib with all the other magnets and sensors and whatever you have around. And then you can make plots like this if you have enough time to do the styling. Yeah, and then there are also compound magnets. These are quite advanced concepts that you can do when you want to have advanced subclasses of the collections with dynamic properties in terms of magnet shapes and a number of magnets. These concepts, again, I just refer to the webpage. And of course, this object-oriented interface is quite nice, but sometimes it's also limiting. Yeah, it's just often not ideal to have objects and paths and when you look for certain solutions or when you want to make magnetic field computation. So we have what we call the direct interface that gives you direct access to compute for a set of input instances. Like here, you just say you want to compute for cuboid magnets, then you give observer positions, you give respective dimensions and magnetization. So in this case, we have 3 instances, and here the direct interface will just compute the field for those 3 input instances. Of course, there's not going to be any graphical representation in this case, but the advantage when you avoid the object-oriented interface is, of course, that you do not have to initialize all the objects, which will make the direct interface a little bit faster. Of course, this will also require so it will only be faster if you are aware how to fast create arrays. Yeah, so don't create arrays with loops. Just use NumPy, standard NumPy commands. And then finally, there's also the core access. You can also access directly through the core sub package our magnetic field computation implementations. Again, you just give instances to it and you can compute the field. Here, of course, you don't have any position orientation interface. I think this gives a general good introduction to the Magpylib package, what it can do, what it is for. As I said, we are on GitHub. Please join us on GitHub. We are happy for any feedback that you can give. We have an excellent documentation that you will just find if you Google for Magpylib documentation or something like this. And as we said, we are very, very open. We have, thanks to the SAL management, we were able to publish this finally under a BSD2 clause license, which is extremely permissive. Fully permissive for commercial use, for private use. You can make any modifications and distribution as you want. The only thing, of course, we don't do, there's no liability from our side and no warranties. And lately, the downloads have also picked up. I think the resonance from the community has becoming more and more and better and better. And I'm also happy that I'm able to share it here. These are just the downloads, the daily downloads that we have from the I don't know, from Conda or from PyP, I'm not really sure, from one of these packages. And if you go online, you will find that this original Magpylib publication is now starting to be cited quite a lot. These are a few of the examples that people have been using this for. Yeah, so it's there are tons of Halbach arrays out there, designing Halbach arrays, design of atomic lenses. There are field designs for plasma containment, a lot of coil designs out there. And in principle, those are also coil designs, lots of coil designs, signal processing. And recently, there's even a publication out on quantum computation, quantum processor design. But for sure, in the end, it's just some coil designs. Yeah. So the thing is, with Magpylib, you can design magnetic fields very fast and very easy. And if you know, and if you're careful, it will also be extremely precise. I think when it comes to you, there are a bunch of papers on magnetic nanoparticle detection. They mostly use the dipole class because it's just fast and easily implemented. You don't have to worry about it yourself. And yeah, as you can see, a lot has been done here. Now, just let me check the time because. Yeah, so I think I still have 10 minutes. Please correct me if I'm wrong, Tang.
Yes, exactly. We booked the meeting until 4:30. Mean you still have 45 minutes. But
okay.
as we already scheduled, I think we open for the discussion and then we go in more detail to the use case, right? To have some simple demonstration, right?
Yes, if you want to. So in principle, the presentation is not over yet. I just wanted to show a few outlines and give you a sneak preview on the new version. This will just take 5 minutes.
Yeah, please go ahead. Yeah.
Yeah. So uses for Magpylib, from our daily business is what I said before. It's tolerance analysis. Where you have these pole wheels, you compute the field of pole wheels, you want to determine if you have a bad magnetic pole, badly magnetized pole, how do you do this? Yeah, but with Magpylib, to develop such a system, it's to develop a system to create this graphical output and also to create this output, is the field that you see at the sensor. This is 40 lines of code. The computation time of this whole thing is smaller than 1 second. If you want to reproduce such a system with FEM, you're going to it's going to take a long time. And even these small, simple, and easy representations, they tell you what happens when you have magnetization defects, yeah, as they are modeled here. Another problem, and this is what I also wanted to talk in the demonstration later on, is the use for optimization. The computations are just so fast that you can write very efficient cost functions and do global optimization with it. But this is something that I want to show later. I just want to say, it's a linear position system, and the cost of a linear position system depends on the volume of the magnets. If you do such an optimization, we can show later that it is easy to fulfill given requirements with a magnet that has only a volume of 30 cubic millimeter, while state-of-the-art magnets are typically somewhere between 100 and 200 millimeters. It's a cost reduction of a factor of, I don't know, 3 to 5 or something like this. Yeah. Of course, we are not just programmers. Yeah? There's a lot of work. From our side in the background. Yeah? We work a lot on implementations, on expressing the classical, the textbook solutions in proper and stable manner. Yeah, just have a look at this plot. it shows you the relative error when you simply evaluate a textbook solution for the magnetic field of a circular current loop. In the areas where it's red, you have a complete loss of significant figures. The result will be completely meaningless. The result from the textbook, if implemented straightforward, is only good in a very, very close vicinity. It's not even stable on the axis. And these are things that we work on very hard to solve. And another thing, we are also looking for new analytic expressions. In this specific case, the cylinder segment that I have shown before, this is something that one of our students and now co-workers developed for the first time. A year ago, this was published. Yeah, there was no one who managed to find an analytic form for the magnetic field of this geometry. And yeah, we can do inhomogeneous magnetizations in Magpylib by splitting up magnets into a lot of small parts. And because material interaction is in principle not possible, this is what makes it possible. Yeah, so material interactions is one of the main downsides. If you split up your volume into a lot of small parts, you let them interact with each other, depending, on the field that you have. You have an opposing field, then you will move down on the magnetization curve. Your magnet is going to demagnetize, and then in the end, this is what you're going to have. Yeah. This is a way, so this method is called magnetostatic method of moments. It's a way to use Magpylib to also work with material interactions. It's one of the major downsides limitations that we had until now. It's not yet part of the library, but I hope it's going to be in the future. But a lot of development effort goes towards understanding how can we integrate this? How can we integrate this in a useful manner? And finally, it's the sneak preview for the new version 4.1, which addresses the problem that we can only do simple shapes. Because in 4.1, we're going to reintroduce the triangular facet class and also the tetraeder, which is basically just a derivative. But think about it. If we can compute the field that is generated by a facet, then any complex shape that we can, so any complex shape from which the surface can be made into a set of triangular facets can then be computed. And basically every shape, you can do this with every shape. And there's a huge synergy here to packages like PyVista. PyVista allows you to create complex shapes even by cutting different bodies. You can see it down here. It's a cutout. It's a spherical cutout from a cube magnet. And PyVista then creates automatically, we have nothing to do with this, then creates a surface mesh, a triangular surface mesh. And we can take this surface mesh directly as an input argument for our new facet class that will be part of version 4.1 and compute the magnetic field, which enables us now to compute the magnetic field in principle for arbitrary shapes in the future, in the near future. And so with this, I'd like to thank you for the attention. This was the introduction to Magpylib and to some of our work. I really want to give credit to my collaborators. Before all, it's Alex Brossolet. He's really the main software developer and mainly responsible that we have such a beautiful interface. Yeah, Lucas did the original software engineering, and he's now he used to be a student, is now gone. Florian and Peter, they are both working in our group. They're working on analytical solutions and numerical implementations. And I really want to thank my the Silicon Austria Labs, my employer, because they let us do this as an open source contribution to the public. If you want to support this project, please go to GitHub, help us out, give us feedback. We love to get feedback, so we can improve the package. Something where you have the feeling, I don't know how to do this, or this seems inconvenient. We really like to get this kind of feedback. And if you want to work or study at the Silicon Austria Labs, please apply. Or if you're interested in this kind of work, also write me an email directly. If you want to do a master thesis or something like this, I don't know. So basically with this, now I'm done.
Thanks, Mikkel.
I'm open.
Very exciting talk.
Thank you.
Fantastic. I wish I came back to my childhood. I went play with this, yeah, because the most exciting time when we see the first time when we see the magnet and see how it interact with other. I think every of us really can imagine when we go back to our childhood when we see the first time we see the magnet and see how it interacted. Thank you very much, Michael. Really exciting talk.
Thank you.
Now, yeah, we can give the question to Michael, and then we will set like a 10-15 minutes that Michael can demonstrate 1 or 2 examples that to show you how the package work. Any question from audience? Anh Khai, please.
Yes, thank you for the very interesting talk, and especially you donate this software to for free to use for anyone. I'm just curious that so you can calculate the magnetic field for. So in principle, you can calculate magnetic field for arbitrary paths, right? For any that the object can move.
Yes. Yes. So if you mean if you have an optic and you want to determine the position of the optic.
Yeah, it's like if you have a sensor and then if the magnet is moving around, you can calculate the field that caused by it moving.
In fact, when you have precision optics, so when you have precision optics and precision optical tables, then you're going to have magnetic systems because they have these ultra high resolutions and are completely decoupled from any optical parts.
Can it also calculate like the current caused by the moving of this magnet?
The what?
Like the electric current, because when it's moving.
No,
for example,
it's pure magnetostatic field computation. You can, of course, compute the current from the field, but you would need extra codes for that. So you would need to determine, basically what we can give you is the magnetic field. When you move your magnet around, you get the magnetic field as a function of the time. This allows you then, of course, to compute the time derivative. And if you have the time derivative, that enables you to compute the eddy currents and the induced currents. But this, of course, you have to do by hand. Magpylib is only doing magnetic field computation.
I see. Because I was wondering, the people who design, for example, magnetic lens, for example, they had a current running in the coil, for example, and how can they use your software to design that to make like to focus electron in something?
Yep. So in principle, when you have a coil, then it's an AC coil, then you can use the library. It's just a current filament field. So you can very easily and very fast create approximations of the field. You will not be able to compute complex current distributions at all. This is not possible at this point in time, and it's also not a goal at the moment. But if you want to approximate fields very quickly, the field of a homogeneous current on the outside is the same as if you have a current filament that is in the center, that is placed in the center of your wire or whatever you have. So it's really practical for fast and quick design to make preliminary estimates, and then in the end you are going to have to use FEM anyways. So I think that the best use for Magpylib is as a pre-stage to FEM to find good spots, and then you use FEM to go really to the optimum. But then you're already in a good spot.
I see. Yeah, interesting. Thank you.
Yeah, thank you.
Any other question from Chị Giang and your group?
Yes, it's very interesting. I have 3 questions. The first one, that's is there any limitation in your tools when we have the different dimension. For example, when I use ANSYS Maxwell, I have very thin thickness but very big area, because for our sensor sometimes I have the design like that, and by using the ANSYS Maxwell it's very difficult for us to make the very fine math. So for your tool is okay or not?
It is okay, but you have to be aware that you need to deal with demagnetization. If you're working with thin films, you know what you're getting is always the field of a homogeneous magnetization. But if you have a thin film, then the magnetization will not remain homogeneous because of material interactions. So you have to use the method of moments. But if you do thin films, I would advise you to use micromagnetic simulation software like OMF or MUMAX.
Okay. Okay.
This is what, because Magpylib, you know, is macroscopic. There is no exchange interaction, involved. You don't have domain formations here.
See, okay. Also the second one, because for some our applications, sometimes I have to integrate between the magnetic sensor, the magnets, but also the concentrated magnetic circuits. It's usually like soft magnetic materials. So I wonder that's by using your tool. So do you have any specific requirement for the tool to use that?
Well, you can always. So I think you can always use the tool when you don't have soft magnetic materials around, and when you do not have to, when you're not so small that you have to worry about domain formation.
Yes.
So the tool is I think excellent if you have, let's say, micrometer and above sized magnets, let's say 100 micrometers, when you don't have to worry about domains. And they have to be hard. They must be hard magnetic, no soft magnetics. You can do soft magnetics, but if you do soft magnetics, you have to use the method of moments. I'm happy to share the codes if you're interested.
Okay. Okay, and the third one, Tom already shared the information about his thesis topic. He focused on the bio detections. So I see in your slide that you can use your tool for magnetic particle detection, right? Can you say a bit more detail about that?
Yeah, absolutely. You know, we are personally not really doing this, but in principle, a magnetic particle, I mean, it depends on how small it is, but that's, let's say, some kind of nanoparticle, you can easily approximate it with a dipole. You know, it's just a dipole. And basically, the field of the dipole is the same as the field of a sphere, but the dipole is also implemented as a separate class. And the thing is, when you have magnetic nanoparticles, then and you want to compute the field from the nanoparticles, then you just use let's say the spherical magnets and you drop them down. I don't know if you have some microfluidic channels or however you move them. And this is going to allow you to compute the field of those nanoparticles depending on their magnetization. So and the best part about this is you can arrange the nanoparticle very easily. You can make it move around, you can make it rotate, and this will tell you immediately what kind of field response you're getting. So I think it's very, very practical for modeling the nanoparticles. And so you don't have to worry about implementing on your own all these rotation and relative positioning. Yeah. So I think for this is what it was used.
Yes, okay. Thank you.
Thank you.
Mikhail can share, as he mentioned, he can share some code which is not really published yet to use. Zhang, if you are interested in. Also opens any questions raised after. Also, the student and your group, if any student interested in, they can really contact Mikhail.
Absolutely, anytime.
Yeah, anytime he can answer any question. It's really nice of Mikhail. Also, yeah.
You know, I don't know is also an answer.
Yeah. As Mikhail mentions, there also the chance that student can come to his lab to do master thesis. The concept of the master thesis here is very easy. We have the project, we open the position to hire a student to work, and we pay salary. to cover enough expense for students to stay at least within 6 months to finish the thesis. And you can call supervisors, students from your group also together with Mikael, and we exchange not only the knowledge, also we can think about the collaboration within scope of the project and the future collaboration. This is very important, and Mikael already mentioned at the very beginning, there's always a chance for young students to go to his lab. Any other questions?
I would also be happy to schedule a brief get to know each other for half an hour to an hour where we just share what we are working on.
This is perfect, Mikael. For the deeper and the detailed discussions, I go to arrange a follow-up meeting really in small working group for those who really interested in this. Is it okay for you, Mikael?
Absolutely.
Yeah, and Chị Giang and then other colleagues who's interested in this topic.
Yes, I have one more small question.
Please, yeah.
For exchange students, for 6 month exchange students, so do you have any requirement for students?
Mikael?
They should be technically competent. Ideally, they should know Python. Ideally, they should have a magnetic background. So magnetic background would be quite required. Yeah, we are also happy to receive students when it comes to systems design. Putting together macroscopic systems like, things like these, where you have system integration, sensor integration, and putting it all together, making it look nice and making it work.
Okay, that's good.
So one thing I got to emphasize is Mikael group, they really working on this from TL2 to TL5. And 6 really go to the demonstration, or even higher, right? You co-develop this device with industry can really go to higher level. The device from the concept to prototyping. You can see that where to bring our idea innovation from the lab to the industry to serve our society. It's still the gap, really big gap. But here in Silicon Austria Labs, especially in Mikael group, they already established this very high level of the sense of the research from the concept to the prototyping. Really, that's why they attract a lot of industry to collaborate with.
Yeah.
That's nice.
Any other questions?
Yeah, I have
Raya, I think it's cool. Yeah.
Go on, please. Yeah.
Yeah, thank you, Miken, for a very nice talk and very nice of you. So I just follow up. I think in Vietnam there are many students, they want to go abroad and want to join your group. What kind of support? So could you please detail that? For example, the salary or anything else, and especially within Europe, it's easier. But from Vietnam to Australia, it's not easy. For example, the cost for airplane and something like that.
I think travel and accommodation. So travel will be paid for by SAL. I'm sure that this will not be a problem. The students will receive a payment of the order of, let's say, 1,000 euros per month, but please don't, it's the order of magnitude for 6 months. But this will definitely be enough to live in Austria. Probably living costs are much higher here. With 1,000 euros, you can get by very well. And so you get a 6 months contract. It's a 40-hour contract. You have to, as a student, you have to work for 40 hours, and travel here and travel back will most likely be covered by SAL. And we would be happy to receive students, good students for sure. And of course, it's mandatory. I mean, good English is mandatory.
Yeah, of course.
Otherwise, you will not be able to get around. Even with just English, it's not so easy. Sometimes I have to confess, since Villach, where we are located, it's not a big city. But you should ask Tang about this. I think he can tell you everything about the strange foreign experience.
Yeah, I think 1,000 Europe. I think it's quite high compared.
Is it net, right, Mikael?
It's also a lot for Austrian students. I don't understand why not more Austrian students apply here.
Yeah. Because I remember for PD support from Vietnam, normally it's just around less than 900 euro per month.
But this is 1,000 mean after tax, right, Mikhail? I don't remember.
Yeah,
from
I
my
think so.
student
I think
before.
it's I think it's just the order of magnitude. But this is maybe it's a bit less, maybe a bit more. I don't know. I would have to
I
ask.
think it's around 1,400 something per month without tax,
Okay.
and after tax you have less. But yeah, for sure it's more than enough. Also cover the transportation. I think it's quite nice. Yeah.
And of course, you need to have an interview before that. Of
For
course.
sure.
Absolutely.
Yeah. Thank you very much.
And Cường.
Hi, thank you so much for the talk. But I am so sorry I would not follow your talk because I already that the workshop will start at 10 p.m. The Vietnam.
Cường, we can't hear you well. Can you check the microphone?
So can you hear?
Can you repeat?
Can you hear me?
It's better.
Yeah, it's better now. Yeah.
Now it's better.
Better now. Yeah, please. Yeah.
Sorry. Okay, so I can talk now. I could not follow your talk from the start, so I don't know in your talk you talk about the magnetoplasmonic phenomenon or not. But now I'm very interested in the magnetics based on a magnetoplasmonic phenomenon, and I am using ANSYS numerical to do some simulation for magnetoplasmonic. And in this software,
Cường, sorry, we also still can't hear you well. Maybe you just stop the camera, and then just maybe the connections from the side not so good. The other way that you text us, text from the chat box, and then we can see the comment. Okay.
Okay, so maybe the point from me in notebooks, I will text.
Now it's better, Cường, I think. Without camera,
now it's better.
Yeah.
Okay. Okay, so hi, Nico. So my question: do you have any experience to do some simulation for magnetic sensor based on magnetoplasmonic phenomenon?
Based on what?
Magnetoplasmonic phenomenon.
Plasmonic.
Okay.
No, I don't think so. I don't think I am aware in detail about the effect, but in any case, you're really talking about
they're in micro scale. Yeah, exactly.
It's micro nanoscale effects, and it's not really something we cover.
Oh yeah, okay. So because I see that now there is a new type of magnetic sensor, very sensitivity to the small magnetic. It is a magnetoplasmonic sensor. Yeah.
Through some plasmonic resonances.
Okay.
Yeah.
So
I'm not aware of this. I have to confess.
Okay. So if you know any person know about the magnetoplasmonic sensor, because introduce to me, because at the moment I also don't have any experience to do the simulation for magnetoplasmonic sensor. So I really need someone can help
Okay, this is something we can try to figure out, and I can come back to you about this.
Okay. Maybe I did, yeah, the right. Maybe Cường, you can contact.
I just want to give a comment to Cường that you didn't attend the talk. The last two talks given by one Vietnamese scientist in US, Professor Tho. He worked about the plasmonic magnetoplasmonic sensor, and he gave a very good talk about that topic. So if you want to know about magnetoplasmonic sensor, maybe you can look for the papers of Professor Tho.
Professor, so
Tho
can
Nguyen,
you give me a
from University of Georgia in USA.
You can also go to the website, our website, and hit recorded talk
Exactly,
in
yes.
the website. You can
Yeah, his
follow
talk
the
is safe in the website.
Okay, thanks. Yeah, Cường, please, yeah, we can go back to the question in detail, but you know this for a magnetoplasmonic sensor or magnetoplasmonic materials, is it really nano micro scale, really sub 10 nanometer scale, and this is for the package Magpylib is really for macro. And yes, if you're interested in, you can contact Mikhail. He can give you the solution, but it really requires multi-physics, for example, FEM and other that you can combine optic model together with yeah, IF and also magnetic model. Then you can model it. Yeah.
Yes, of course.
Okay. And now we have only 15 minutes. I would like to give the time to Mikhail so that he can show us how it works.
Okay.
Thank you very much, Mikhail.
Okay, well then, thank you. Then I will continue with. I promise that I will give a brief live coding session, and I actually planned it for 30 minutes, but I can at least start on it so you get a brief introduction. And I've looked for a really nice example that I spent many years studying, which is the shift fork in any kind of car. So when you have a gear shift in your car and you move the gear shift, what happens is you switch between different gears. Yeah, so you know, the motor is rotating, and then depending on whether you have the first, second, third gear and so on, then you do have different transmissions. And in order to determine the position of the gear that you have locked at the moment, this transmission is moved around by gear shift forks. Yeah, it's this part over here. Yeah, this is the gear shift lever, and a shift fork typically looks like this. Yeah, these are all photos taken from the web, and the way the position is detected on a shift fork system, you know, it's a linear position, it just moves back and forth, is through magnetic sensors. And you can see it here directly. You have this arm, and over here you have two small sensors integrated. And if you look only at this part here, it's in principle this. Yeah, it's just two magnets. They are housed somehow, and then over here, so is placed a sensor at a certain distance. And from the sensor output, you want to determine the position of the shift fork. And when you have such a system, then you also, you know, you have some specific requirements in terms of how much motion range you want to cover. For example, you want to have 20 millimeters or so. This would be a typical motion range in such a system. And you want to use some kind of differential measurement device. So you have a sensor that actually has 2 pixels and then measures a differential field. And based on the differential field, you then compute the position of this magnet system. Yeah, these magnets that you have in here, they have typical volumes of like 100 cubic meters, and the air gaps are of the order of, I don't know, 2, 5, 7 millimeters, something of that order of magnitude. And the goal would be to compute a system that is as cheap as possible, where you fulfill certain fundamental requirements, like a certain resolution that you want to achieve. You don't want to have more than this. You want to have just this kind of resolution, 10 magnetic degrees per millimeter. And you want to have always at least 10 millitesla field amplitude on your sensor. So those are, let's say, constraints, requirements that you have. And under those constraints, how cheap can you make your system? And cheap now means you have a given sensor, no choice about this. So you can only reduce in magnet volume. Yeah, small magnets. So magnets are typically a little bit the bottleneck in the magnetic sensor systems because they are quite expensive. Yeah. And in this specific case, we want to just reduce the magnet volume as much as possible. And so we choose certain design parameters, you know, like the air gap, like the magnet dimensions, A, B, C, and the distance between the magnets. And we vary those parameters and we try to find a solution based on constrained global optimization. And for this demonstration, I have chosen this side-by differential evolution algorithm because it's accessible to everybody and it just works really well. And yeah, so then let me just briefly switch to the program. I will not manage to do the whole thing in 10 minutes, but maybe we can start in 10 minutes and that will show you that in 10 minutes I will be able to guide you through the fundamentals. Yeah. So I'm just importing the respective packages that I need. Of course, I want to have NumPy. And for plotting, I definitely want to have Matplotlib pyplot. Yeah. And yeah, then in my system, I definitely have some kind of air gap, and the air gap should be, let's say, 5 millimeters to start with. So first I start to design and outline the system. Then I want to have some kind of range, or we often refer to it as the stroke, and the stroke should be 20 millimeters. And then I just start off with some simple magnet sizes. I just give dimensions A, B, C for 4 millimeters. Yeah, I want to have some kind of sensor. Yeah? I call it sense, and it's just a Magpy sensor object. And initialize the sensor object, you can see that you have these nice tooltips. If this is now in the Visual Studio Code environment, but you're going to have this in any kind of development environment, which will tell you what are the arguments of your, or what are the properties of your objects. And in this case, for the sensor, you have as usual position and orientation, and also the pixel in case you have a multi-pixel sensor. But if I don't put anything, the sensor will be placed in the coordinate origin. It will be oriented along the coordinate axis, and I only will have one pixel directly in the center of the sensor. And then I just want to have, let's start only with a single magnet, not two magnets. This will maybe take too long. I define a magnet through the magnet subpackage, and it should be a cuboid magnet. Basically, it can be pick anything. You look again in the tooltips. What options do I have here? Aha, okay. I need to give magnetization and dimension at least, and then maybe also some kind of position orientation. So for the magnetization, we just choose like Z magnetization 001,000. This is typical for neodymium iron boron magnets, and then some kind of dimension, and the dimension should just be A, B, C, whatever I choose. As I've chosen as input parameters over there. Yeah. Now this magnet should move over the sensor. Yeah. So it should fulfill this kind of motion. Yeah. So now I only have a single magnet or two magnets, and this magnet should move left, right. So what I do is I just go. I just access the position attribute directly, and I just set it to a path. And in this case, the path is very, very easy. I just use a linspace commands from NumPy. I start at so I'm moving in X direction. So I have stroke over 2. So I want to start on the left. In Y direction, I want to start at 0, and in Z direction, I just want to start at the air gap. And because the air gap moves me to the center of the magnet, I also want to add half of the Z dimension. And from this position, I want to move to the other side. This is at stroke half, 0, and again, gap plus C over 2. And I want to do this in, I don't know, 100 steps, why not? Yeah. So I just set the cube position to this path over here. And this is already the point where I'm kind of done. And I want to see, have I done it correctly? You know, I have a magnet, the magnet moves over the sensor. I want to see what I've done. So I just go Magpy show. I want to see the sensor. I want to see the cube magnet. and I don't really care about the backend. Yeah, so I just do it like this. I compile it, and I should get an output immediately. Looks like this. Yeah, so this is now in Matplotlib, and you can see the magnetization is shown by this magnetization vector. You can see here the path, the magnet moved from here to here, sensors below. So I think this looks quite decent for whatever we want to have. Now, stop this. I compute the magnetic field. Tooltips tells me first I have to give a set of sources, then I have to give a set of observers. The sources are in this case the cube. The observers is in this case the sensor. And that's basically it. And then I just want to use Matplotlib to plot the fields. So I just got PLT, plot B. And this should kind of do it. I'm going to need to show it. And so this should actually give me the output that I would be kind of expecting, and this is perfect. So my sensor moves over my magnet moves over my sensor. I have one component that is 0, which is of course the Y component of the field, and then I have a Z component and I have an X component. And you can see this is a very typical behavior that you have in these linear position systems and in any kind of other, in all the systems that I've shown you today. You have an even component and you have an odd component. And these two components are at least close by, they're quasi-harmonic. So this is now, let me show you what is the big trick that everybody's doing in magnetic position sensing. You take two components, I'm actually just going to transpose this, and then I just go Bx is, actually just going Bx, By, Z. So now I have the three components of the field separated. And so what everybody's doing is that the signal is simply compute this through the arctangent. Arctangent 2, this is just a continuous extension on the whole 2 pi interval. And we have Bx and Bz. And this combines the two components of the field, Bx and Bz, into a single signal. And the signal looks like this. And now you can see this is really something we can work with. Yeah, down here we have the position index. And now you can see the sensor output signal. There's a one-to-one correspondence from the position to the sensor output signal. And this is what you're looking for. And this is how magnetic sensing works. This is basically all concepts that we have are based on something like this. And yeah, and now let me just think for a second how to continue, because I have prepared a bit more.
Nico,
but
I think we can extend it to 10-15 minutes if you need more time here.
I think I will just show a few things and then I'm mostly done. I think if someone is interested, you can always go to the webpage. There's really a lot of material also on the webpage. This is kind of just a bit of a sneak preview on what you can do with the Magpylib. So what I want to show is that, for example, you can do the styling. So you can give individual styles by using this is really nice. You can use underscore magic for this. You can just go style. You can either hand in a style dictionary, or you can just go style, color, and then you can choose, I don't know, orange, for example. And then this will not help, of course. Sorry for this. Yeah, so then you can just style individual magnets in the individual parts. If I would have multiple magnets, I could style each of them individually. I could combine them into collection, but I think maybe this one thing that is really nice to show is the following. I'm just going to show you how to optimize this one. I'm not going to do two magnets and two sensors. Yeah, so just I'm going to eliminate the style because it also creates a little bit of an overhead at initialization. We know our system is good, but now if I want to define a cost function. And the cost function should have input variables. And basically the input variables, I'm just going to use A, B, C, and the air gap as input variables. So I have the gap A, B, C. These are just the input variables. Yeah, so I'm just going to eliminate this, and the stroke can go inside. Then I'm just going to create a sensor. I create the cube all inside of my cost function. I have the Q position. Now we're not going to need 100. I'm just going to use maybe 50 positions. That will make things a bit easier. We compute the magnetic fields inside of the cost function. We compute the signal inside of the cost function, and what we return the volume of the magnet, which is just going to be A times B times C. And what we now want to do is we would like to optimize this cost function, meaning we want to minimize the magnet volume under certain constraints. So under certain constraints that we want to implement. And one of the constraints has, of course, to be that that the slope, the slope must be more than 10 magnetic degrees per millimeter. So just I'm now introducing the constraints in a very, very simple manner. So I just define the min slope. The min slope is, of course, simply given by I just compute I just use finite differences to compute the differential. Yeah, so finite differences to compute the differential. I take the minimum of this, and I want for the minimum slope. I want for the minimum slope now in degrees, because that this is now going to be given in radian, not in degree. I want, if this is smaller than 10 times, now I also have to multiply with the stroke in order to normalize the step size of the finite differences. Now we did 50 steps. Okay, and so if this requirement is not fulfilled, this is really the requirement, or this is this constraint. So if this requirement is not fulfilled, then the algorithm should, then this cost function should just return a large number. And then there's a second constraint that means that the field amplitude should always stay within a certain range. So this means the always above, let's say 10 millitesla. I honestly have to say I'm not 100% sure how this will turn out, because this is not exactly the problem that I've prepared. So the minimum amplitude is, of course, simply given by and I would like to use the norm, but now we transferred it over here. So we have bx squared plus bz squared square root. Yeah, so this is definitely going to be the minimum field amplitude at any spot, and that minimum field amplitude should always be if this is smaller than 10 millitesla, then I would say we want to return a large number. And if it's not, then the system is feasible. And if it's feasible, I want the cost function simply to return the volume. And this is now a cost function that will always generate the system. It will compute the respective quantities. It will check, are the constraints fulfilled or not? And if they are fulfilled, it will return the volume. And this is a cost function we can now use for optimization. We can plunge this directly into an optimization algorithm. And I don't know if you're familiar with differential evolution. If not, I strongly suggest that you try this one out. It has become really nice over the last years. A very powerful algorithm. And it's very synergetic with Magpylib because it's a stochastic optimizer. So you have so you can compute you can compute multiple instances at the same time. it's just perfect for parallelization. And this just really plays nicely into the hands of Magpylib. And of course, it's Python. You get beautiful tooltips, and they tell you everything that you want to do. So the cost function is in our case just going to be the cost function. We are going to have to give bounds, and for the bounds, we just have to define the respective boundaries for our variables. And the air gap should be somewhere between, let's say, 2 and 7 millimeters, and the magnet dimensions, they should be, let's say, between 1 and 10. Yeah, whatever you want to have. So this should in principle already do it, but then the differential evolution, maybe you want to have make sure it doesn't run forever for the first tryouts, and you also don't want it to polish, which runs just an additional local optimizer at the end. I'm just going with a small number of iterations, and yeah, I also want to see what it's actually doing. Yeah, so I'm just going to run it and see if anything comes out. I hope this will actually work out now. But I don't get any results. So you can see that for all these input parameters, what the differential evolution algorithm is doing, it is really attempting to create. So it creates a Latin hypercube inside of the bounds, and then it's testing on a lot of designs. Do I find any possible solutions? And based on the designs that I've now provided, based on these requirements, we do not find anything. Yeah, this is probably because some of the requirements are too strict. My guess is, since this is a requirement that was designed for differential system, it might be that that's the requirement that is too strict. So, so based on this, I'm just going to reduce this requirement a little bit and see if we can get it to run with this. And yes, actually we can. So that requirement was a bit of a strict one, but now I think I can already really nicely demonstrate the whole point of this. Yeah, I have now been at this for, I don't know, 15 to 20 minutes, and yes, I've been doing this for a few times. So this is common territory for me. But you can see that we just have a few lines of code to create a system, few lines of code to create the magnets, and we have a cost function. The evaluation time it takes for this cost function, we are really talking about microseconds here, with all object initializations and everything. Yeah, the differential evolution algorithm with 4 variables, it has a population size of 15. This means it computes 15 times 4 number of states, with random states within the volume defined by the boundaries. And based on this, it then chooses the best one, and then it goes to the next step. So each time one of the steps is computed, we have, I don't know, 50 system computations. And a single system computation requires 50 field computations. Yeah. So you can imagine really how fast this is. How fast it is that it enables us to make these differential evolution computations with so little effort. I'm doing it on my laptop. I'm only using a single core. And if I want, and this is also where this algorithm is really nice. You can just tell it to use multiple cores. In this case, it would actually, you probably need a multiprocessing guard also, because in Windows things are not so easy. Okay, so this is just a multiprocessing guard, and I also include the maxiter by a lot. And then you see now this should be like really fast. And there are still a lot of ways to improve this in terms of performance and everything. But you can see how performant this algorithm is. And this is 4-dimensional optimization that you see here. The resulting air gap is as small as possible. You want to move the magnet as close as possible, and the magnet also hits the boundary. So in X direction, it is very, very long. In Z direction, it's very, very short. And in Y direction, it just goes to some kind of area right in between. Yeah. So this really tells you a bit what magnets directions are favored. You know, what is favored. This is what these algorithms tell you, and what these optimizations tell you. And just imagine, just imagine for a second, you have to do to solve such kind of problem with a finite element environment. It's just not feasible. Even this simple problem that takes me 20 minutes to solve on my laptop, it is not feasible to do this with finite elements. Four-dimensional optimization is hard. We can, with this method, we can easily go up to 20, 30 dimensions. And if we go to 20, 30 dimensions and we do this on not too extensive computation, if we go to our servers where we can have, I don't know, 100 or even 1,000 cores if necessary, we can do quite, we can cover quite a lot of ground. I think this kind of concludes my presentation. I hope that was also interesting and gave a little bit of insights into Magpylib and into the advantages of Magpylib. And if you have any questions, really feel free to contact me at any time.
Thank you very much, Mikhail. Wow, thank you very much. Already 2 hours you stayed with us, but we're still open for 5-10 minutes discussion. If any question from the audience, from the colleague.
Mm-hmm.
Any questions? Yeah, for example, Hoang-Tâm, in the future, if you wanted to create kind of like a microfluidic channel, but using nanoparticles, that's but you also wanted to use magnet to either you wanted to select magnet nano magnet or nanomagnetic material, a particle. You can think how to arrange as macro magnet mean around the microfluidic channel to control nanoparticle. I think it would be also the option. Yeah.
Let me tell you about the nanoparticle. Why the nanoparticle is really interesting. So you have a microfluidic channel and you have a sensor or multiple sensors around the channel, and then one of these nanoparticle passes through. Yeah, it passes through somehow. It has some kind of magnetization that you don't know. It has some kind of magnetic moment that you don't know. You only have the sensor output, and now you have to try to find out what kind of nanoparticle is this. So what you do is you create a cost function like this one for the nanoparticle. You have a bunch of variables that are the magnetic moment and the direction in which the nanoparticle points. Yeah, and then you just run the optimizer to find out what have you just detected. This is what you can do, and this will work very good if your sensors are good.
Wonderful. Hoang-Tâm, yeah, if you have any question, this is really, he answers the question in the future, I think.
Yeah, very interesting, but actually I don't know anything about this simulation, so sorry, I don't have any question now.
Take your time, yes, because I know you're very good in programming. You work in the Global.com of our university, so you're very good at this. So take a look, and you also, yeah, once you go in this, and just take a kind of like case study, and you wanted to design sensor, this kind of sensor, and let's start with it. And if you have any questions, just contact Mikhail. He can give you suggestion. Yeah,
absolutely.
Yeah, thank you. Yeah, thank you very much.
Hi, Anh, may I have a question, please?
Go, please. Yeah.
Thank you, Mikhail. It's very nice. Unfortunately, my topic is quite far away, your topic. But I would like to ask you one question. I don't work with nanomaterials, but I work with laser and light. I just wonder if a laser light go through some different kind of magnetism, it did change the polarization of the laser light. Do you know anything about that?
Yes, we are very interested in this. This is actually very good for magnetic sensing. This is also used in the MOCA. I don't know if you're aware of this magneto-optical Kerr effect. So there are groups here, there are companies here who produce sensors based on lasers. And we are thinking to collaborate with them. We just never managed to bring it really to roll. We have very good laser optics here in the house.
Yeah.
And in terms of materials, it's really interesting, especially if you have some kind of scanning optics. The thing is with if you have a laser scanning optic, then you can detect the magnetic field very nicely. So it has a huge advantage over, for example, magnetoresistive technologies, because with magnetoresistive technologies, you always have these soft magnetic materials. And in principle, a sensor always kind of influences the field, and you never really know what you're measuring. But if you have an optical design to measure the field, it's just very powerful because it's completely decoupled from magnetics. And all you do is you see the change in polarization of the laser, and you measure it, and they are common. So not common. They are known effects. Kerr effect and Faraday effect.
Yeah.
They are very well-known effects. But to bring them to sensors and to special sensor solutions, I think these are ongoing efforts. We are also interested in this. We are very, very interested in reconstructing magnetization pattern, not on the micro scale, but on the micrometer scale.
Yeah.
And optical measurements here are for us actually quite interesting. So if you're working in magneto-optics or with magneto-optics, I think that would be very interesting also for us.
Yeah, I only work with spectroscopy.
Mm-hmm.
So I use in laser to develop, combine with optics to develop spectroscopy, different kind of spectroscopy.
Mm-hmm.
So I don't work with magnetics before, but I think it's interesting, and maybe I read more paper, and maybe I will for some question or idea later. Yeah.
Absolutely, we are always happy to collaborate.
Yeah, thank you very much.
Thank you.
Also, Mikael, Kung also now she's an assistant professor in Lund University in Sweden, and also Professor Anh-Diệp. Yeah, we can also think in the future, if you have any idea or think to establish kind of a small consortium, we can also think, find a good idea, brainstorming that we can apply for funding. This is quite easy within Europe. But,
it's always easy to apply.
Yes, of course.
It's hard to get the funding.
Own way. Yeah, that's
another story.
Fishing.
I think honestly, I'm sure that we would be quite interested also in magnetic optic corporations. Multidisciplinary is always interesting and also much easier to apply.
Yeah,
exactly. This is our team. It's really like this. We have many experts from different fields. I don't see any further questions from this colleague. I think we stay almost 2 hours. Very interesting, exciting discussions. Once again, thank you very much, Mikael, for joining us and give very nice talk. We could imagine how to bring our innovations from our idea from the lab, from the mind, from the head to the real practical application to answer the need from industry, to answer the need from our society. It's very important for any kind of research, for any kind of motivations to do research. Thanks, Mikael.
Yeah. No, thank you, and I'm really very happy to participate.
Yeah, and may I have a little bit comment? Yes, so I think it's very interesting and valuable talk. Additionally, it's very complicated for other people, I think.
Yeah.
Because you spend many years to develop that, and now you talk within 2 hours. So I think we need to rewatch the video. And as Anh Thắng suggested that maybe some students, if they are interested in more, they can contact Anh Thắng to arrange some small group. And
I would be very happy to make a workshop with the group as an introduction to the software. What you can do, what you cannot do, when you can use it, and how you can use it.
Yeah, I think the workshop will be perfect, Anh Thắng.
Very important also for students. Chị Giang, also anh Hải, anh Tuấn from Liquidon Technical University. if you are interested in, really can make a group that a student can. Yeah, Mikhail can also join, or he can also yeah, serve as invited somehow, like we have the kind like joys program or joys lecture, something like that. Chị Giang, yeah, you can give some lecture, some credit to student if you're interested in this.
That's a good idea. Yeah.
Not only is this, it's you see when you do this, you get involved in this Magpylib, you also learn Python, you also learn to do other things.
Yeah, maybe in some chị Giang, in some lectures, in some course you are teaching, maybe you can include some lectures and invite the midcamps. So I think it's very good idea.
I'd be most happy.
Yeah, that you see that we can always happy that to bother him. Thanks, Mika.
I have a lot of courses prepared because I also teach at a local. I used to teach at a local university for applied sciences, and also I use Magpylib to teach in their classes.
Yeah,
wonderful.
Great.
Also, Phan Anh, today you can't interact with us, just listening, but I hope that you will give a comment, or really we can also we can create a kind of working group that to work on different programs. Also, Phan Anh, I know that you're also interested in, and also a lot of idea already came in your mind. I hope, and we can really create a new working group to deal with different programs. Okay, any further comment?
That's a quick question, a technical question to Michael. From your optimization, I'm just wondering, so when you plot the results, it's like maybe it's the magnetic field. It's not a linear function, but it's like a curving function. So this it might be a bit difficult to calculate the position. Is not a linear function. So can we optimize in the way that it will be a linear function?
Yes, you're quite right. This is a big topic. You always want to be linear. In principle, what I also do most of the time, I add another constraint that says make it as linear as possible. So depending on what I want to do, I change the parameters of the computations in such a way that I always get what I want to have. And making the output linear is one of the main challenges. But it's absolutely possible. I can just add it as a constraint, and the program will look for a solution that is very, very linear. You just have to, in the end, you just have to choose what do you want to put your focus on. You know, do you want to have less magnet volume? Then it's going to be more difficult. If you allow for more magnet volume, but you want a higher grade of linearity, you know, you always have to keep the balance somehow. But in principle, we even published papers on how to make signals linear with different magnet shapes.
I see. And from this function, like what differential evolution, can you get the uncertainty with the parameter?
Sorry?
Can you get the uncertainty of the parameter from this optimization?
Yes, absolutely. Okay. You mean now for the optimization that I just showed, or?
Yeah.
Here basically I just print the results. I can also, if you're interested, I can also display it graphically. But this is basically the result that comes out from the differential evolution. It just tells me, okay, my air gap should be small, 2 millimeters. It tells me the X dimension of my magnet should be large, 10 millimeters. Then the Y, this is the Y dimension, this is the Z dimension. You can see that I run against two boundaries. I set a boundary of 2 for the air gap, and I set an upper boundary of 10 for the magnet dimension. And this is where the differential evolution already hit. I'm sure I can get a much better result in this one if I increase this boundary, for example, to 20, just to make it much larger. And I would even make it better if I could reduce this boundary, but going beyond 2 millimeters is not realistic. You know, in a real system, you need to have a distance between the sensor and the magnet. And now you can see that the result, it already goes down to 35 before we were up at 80. So now we have already reduced the volume by another factor of 3. And now you can see, okay, I don't touch any boundaries. I have a very, very, very long magnet. It's very, very thin. It's a very strange solution. And now it also doesn't hit on the low on the air gap below.
Yeah, on the boundary. Okay.
But this magnet volume is minimal. But now of course you understand, of course, that now you have to make things that make a lot of sense. You can add more constraints. Linearity it's a big issue. But in principle, what I also understand nowadays in modern sensors, they in modern sensors, what is often integrated is a multi-point calibration, where you just make a linear interpolation between multiple points, and then the linearity doesn't matter so much anymore. And the second thing is, very often you can add some coefficients and make a polynomial fit. And then also a quadratic fit or a cubic fit, then you also don't have to worry so much about linearity. So linearity is a nice to have, but even in automotive, where you want to have the cheapest possible, it's not an absolute must anymore.
Yeah. Yes, I get the main important the cost. It have to be cost effective, and if it's linear, then probably it costs less. You don't have to put more equipment to calculate.
Yes. It reduces cost. Yeah.
Right. Okay. Thanks.
Thank you for the question.
Yeah.
Thank you. Yeah, what I would also to highlight it from you see from the quote from Mikhail. He never think about really complicated thing. Yeah, everything he tried to minimize to simplify it. And also you see the sensor that uses in automotive from some industry that he has collaborations. Really, Really is the biggest name in the automotive sensor over the world. They also provide sensor to VinFast. But Mikhail can use this tool to design the sensor, position the sensor. Also can use this tool to design like joystick and other sensor for automotive sensor. It really amazing. Simple tool can do the great thing.
Nice.
You just have to be careful. When soft magnetics are around, you don't want to use it. It's always good to make, in the end, a test with the FEM to be sure that you're right. But also the other way around, you know, when you make a FEM computation, it's good to check it out with another method, because computations, you never know. In the end, you never know what you have, and it happened for sure to many people so far to use the finite element environment to click on the button "Start my computation" to get something out that looks good but is completely wrong.
Exactly, and it takes a few days to get the answer.
Yeah.
Okay, if no more questions, so I would like to close our seminar today. Many thanks to Mikhail. I wish you a nice weekend, and wish all of you a nice weekend. Audience, very nice discussions. So looking forward to our next seminar. Bye-bye.
Thank you.
Thanks a lot. And thanks for the invitation.
Thank you, Tom, for
Just reach out to me or Mikhail if you have any further questions. Yeah. Thank you. Bye-bye.
Thank you.
Bye.
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 Bye-bye.
Bye.